Hello everyone. So far we have gone through the Bishop's effective stress principle, which is modified after Terzaghis effective stress principle for the unsaturated soils. Bishop introduced one more strength parameter called effective stress parameter XIF, which is function of matrix suction. The estimation of XIF function from the suction control direct shear tests and suction control triaxial tests are seen. So today we will understand the development. There were some more developments that took place later on, because the XIF parameter estimation is very difficult, especially for fine grained soils where the estimation of XIF over a wide suction range is very difficult. So independently there were some more tests that were conducted by other researchers further to evaluate whether the independent stress state variables that were used by Bishop are valid or not. So such tests are called null type tests, so which we will discuss today. So the null type tests, these tests are to understand the validity of different stress state variables. So it is based on manipulation of different combination of stress state variables. Changes to either total volume or degree of saturation is observed or used as the measure for understanding whether they are independent stress state variables or not. So null tests are conducted by Friedland and Morgenstern in 1977. This is very popular work, and the concepts are used even till date. So this is published in ASC Geotechnical and Geoenvironmental Engineering in 1977. So in this work they have conducted more than 19 null tests on compacted kaolin soil, kaolin clay, by controlling different stress parameters. So as in triaxial cell, one can control the deviatic stress, the all round pressure, the pore air pressure and pore water pressure. Of course you have coarse porous stone here, and then you have a high air entry porous disc located at this location. So therefore the UA within the soil mass and UW within the soil mass can be controlled independently. So therefore they have changed these parameters such a way that either all the parameters are increased to the same extent or decreased to the same extent. So here if you observe the test number 23 from their work, so this is the initial conditions of the soil where the soil was at equilibrium. Total stress was 420.7 and pore air pressure is 278.7 and pore water pressure is 109.6. You can assume some units, maybe kilopascal. Now the delta sigma is increased to plus 71.4 by changing the water pressure to plus 70.3 and changing the air pressure to plus 70.7. They want values of these parameters to be the same. So while doing this in experiments, slight deviation was there. However, nearly the changes in the values are constant. So due to these changes, the sample dimension, the sample volume did not change, or the water content did not change during the testing. Similarly, there is another test 25 number. This is initial condition, and so the changes in stresses is same in delta sigma, delta UW and delta UA. Similarly, several other tests data are shown here. Either you increase all of them plus, or you decrease all of them. So in the same direction they have been applied, and when these changes are made, the sample volume did not change. That means the shear stresses are not initiated within the soil sample. So this is because the sigma minus UA there is effective stress, the net normal stress we use, which is equals to sigma plus there is a small increment delta sigma in the test number 23 minus UA. Here UA is increased a small value delta UA, test number 23. So, as this delta sigma and delta UA are maintained to be constant, so they get cancelled. So, essentially you get sigma minus UA. Similarly, if you take UA minus UW, the increase UA plus delta UA and UW plus delta UW, this delta UA and delta UW both are one and the same. This remains UA minus UW due to increase in the stresses as shown here. So, therefore, these two variables can be used as independent state variables for defining the shear in the soils, because earlier Terzaghi had showed that it is the effective stress that defines the state of the soil for shearing, and here Bishop has proposed that sigma minus UA, the net normal stress, and UA minus UW, these two should be used as stress state variables and they are independent to each other, and that is proven by these null tests by Fredland and Morgenstern. So, sigma minus UA and UA minus UW, when they are kept constant, there is no shear induced in the soil sample. So, therefore, there is no change in the volume or degree of saturation. So, these are confirmatory tests for Bishop's effective stress equation for unsaturated soils. Further, their observation states that it is not just one combination of sigma minus UA and UA minus UW to use as two independent state variables, stress state variables. They further say that even if you use combination of, this is one set sigma minus UA and UA minus UW, another combination sigma minus UW and UA minus UW, and other third combination is sigma minus UA and sigma minus UW. Any of these three combinations can be used for defining the stress state in soil. So, here the sigma minus UA or sigma 3 minus UA and UA minus UW are maintained to be 13.8 and 58.6, changing from the initial value like this 44.8. So, 13.8 and 58.6 are maintained, and in the second test same values are maintained, but different values of sigma 3 and UA are given, and similarly different values of UA and UW are given, but the UA minus UW remains constant. So, in these all four tests, the sigma 3 minus UA and UA minus UW are kept constant, then the volume of the sample did not change. So, group 1, that is sigma minus UA net normal stress and UA minus UW, this combination qualifies as independent stress state variables. Similarly, the group 2 is analyzed, that is sigma minus UW and UA minus UW. So, here the same combination is maintained for all different tests by varying sigma 3 UW UA independently. So, then the sigma 3 minus UW and UA minus UW, these two combination kept constant for all these four tests, and even now the volume remains constant. Similarly, in group 3, the sigma minus UA and sigma minus UW are maintained to be constant for all these four tests, then the volume remains constant. So, therefore, the effective stress equation that is given by Bishop, that is sigma dash is equals to sigma minus UA plus xi f or simply xi UA minus UW. This is what we used as effective stress principle, modified effective stress equation from Bishop's proposal, and here the effective stress also could be used as sigma minus UW plus some xi times UA minus UW, or this could be sigma minus UA plus Xi sigma minus UW. So, any of these three combinations can be used to formulate the effective stress principle, and it could be used to define the shear strength of the soil at any given stress state. So, therefore, these tests reveal that Bishop's independent stress state variables indeed valid for the unsaturated soils, and moreover any of these three combinations or group 1, group 2, group 3 could be used as independent stress state variables. Fredlund and Morgenstern, after their stress state variables definitions and stress state variable confirmatory tests by null type tests in suction controlled triaxial and suction controlled consolidation cells, they have come up with new form of modified Coulomb failure criterion for unsaturated soils. Before going into that, let us understand how the stress can be represented graphically, so that the Fredlund's extended Mohr Coulomb theory can be very well understood. So, here the stress representation for unsaturated soils can be understood by solving some problems. Here there is one particular problem that is taken, that is some example. So, one shear testing is conducted on clay soil using triaxial setup. So, a soil sample which is at equilibrium with an all round pressure sigma 3 is equals to 300 kilopascal. So, this is all round pressure, and a deviatic stress of 100 kilopascal is acting. So, this is sigma 3 and that is delta sigma, and there is a pore air pressure on the sample is 200 kilopascal and pore water pressure is 100 kilopascal. This soil state can be represented graphically as we know the stress state variables for unsaturated soils we can choose as net normal stress, that is sigma minus UA and UA minus UW. So, as this is a triaxial test, you will have sigma 1 and sigma 3, therefore, we can draw the Mohr circle. So, this can be plotted as tau on y axis and sigma minus UA on x axis, but as we have suction also, matrix suction also, so that can be plotted on third axis. So, this is third axis. So, z axis for U minus UW. So, if that is represented on y axis, z axis, now the stress state of the soil can be represented on U minus UW is 100 kilopascal. So, this is located at 100 kilopascal here. So, this is 100 kilopascal. The Mohr circle stress circles can be drawn on this axis, so which is at 100 kilopascal on the z axis. So, here the sigma 3 minus UA and sigma 1 minus UA can be obtained. Sigma 1 minus UA, there is a net normal stress in the y direction on the soil sample is 300 plus 100, that is 400, minus UA is 200. So, therefore, this is 200 kilopascal, sigma 1 is 400 minus UA is 200. So, therefore, this is 200 kilopascal and sigma 3 is 300 and UA is 200, therefore this is 100 kilopascal. So therefore there is 100 kilopascal here, and there may be 200 kilopascal somewhere here. So this is this is 100 kilopascal and this is 200 kilopascal. Sigma 1 minus UA is 200 kilopascal. So the maximum stress is at the center, that is 50 kilopascal, and maximum stress exists at 45 degrees from the major principal stress, and this is maximum value is 50 kilopascal. So this is how the state of the stress can be represented graphically on a three-dimensional plot. Similarly, let us take another example. So there is a soil mass which is located at on a slope. So therefore it has three stresses acting: major principal stress, and the net normal stress along the major principal stress is sigma 1 minus UA is 400 kilopascal, and intermediate stress is 100 kilopascal, and minor principal stress is 50 kilopascal. So if these stresses vary during the monsoon state, the stress state changed from one season to another season. This is season 1, and in the season 2 the stress state changed to sigma 1 minus UA is 360 kilopascal, and sigma 2 minus UA is 90 kilopascal, and sigma 3 minus UA is 45 kilopascal. And in the season 1 the matrix suction in the soil is 250 kilopascal. So this is a relatively dry season, and in the season 2 the matrix suction decreased to 50 kilopascal. So how to represent the change in the stress state of the soil? This can be again drawn on the 3-axis plot: sigma minus UA on x axis and tau on y axis, and the third axis is for UA minus UW. So here on the suction axis at 250 kilopascal somewhere here, you draw a horizontal line. So this is sigma minus UA parallel to the sigma minus UA axis. So here on this, the sigma 1 minus UA is 400, say 400, and sigma 2 minus UA is 100, and sigma 3 minus UA is 50. So you have one stress, so this is how it is plotted. So this is so this value is 50, and this value is, this goes parallel to this axis. So this is 100 and this is 400. Similarly, in the other season, season 2, the matrix suction decreased to 50. So assume that this is 50, and horizontal if you draw, and here this became 360, so slightly decreased this value, and here it's 90, and here it's 45. And this is how it can be plotted, stress state of the soil. So in case of Bishop's effective stress principle, we have one test data. So, that is UA is 100 kilopascal and UW is 0 kilopascal. So, in the axis translation, let us understand how the Bishop's modified Mohr-Coulomb equations can be represented graphically. So, let us assume one problem where UA is 100 kilopascal and UW is kept at atmospheric. So, this is 0 kilopascal, and in one test in test 1, sigma 1 is 1000 kilopascal and sigma 3 is 400 kilopascal at failure. These are observed data. And in test 2, when the sigma 3 is maintained 600 kilopascal, the soil failed at sigma 1 of 1600 kilopascal at failure. If Xif is known, which is equals to 0.5, because it depends on matrix suction. So, matrix suction is constant in these two tests. So, Xif will be constant for these two tests. If Xif is known, that is 0.5, then how to represent this? Here in the same way you can represent. On y axis it is a tau, and on x axis this is sigma minus UA. So, now there is a third axis. Now, in this case, because the equation is tau f equals to C dash plus sigma minus UA plus UA minus UW times Xif times tan phi. So, this is intercept plus this whole thing, the one axis is sigma minus UA, another axis is tau f, and other axis could be Xif times UA minus UW. So, this is Xif UA minus UW. Then at one particular Xif into UA minus UW, UA minus UW is suction is 100 kilopascal, Xif is 0.5. So, this is 50 kilopascal. Xif times UA minus UW, that is 50 kilopascal. Then in one test, the soil failed at sigma 3 400 and sigma 1 is 1000 kilopascal. So, this is test 1, 400 and 1000. In the test 2, when the sigma 3 is 600 kilopascal, it failed at 1600 kilopascal, somewhere here. So, this is test 2 and this is test 1. This is how it can be represented, because we have, when we have all the three axes defined, one is tau f, another one is sigma minus UA, and another one is UA minus UW times Xif as third axis, then the stress state of the soil can be very well defined using graphically, by graphically. Now, we can understand how graphically the stress state of the soil can be represented. So, Fredland, Morgenstern and Widger in 1978 proposed extended Mohr-Coulomb criterion. According to this criterion, the tau f is equals to C dash, that is a cohesion intercept at suction is equals to 0, that is at saturated state, plus sigma minus UA at failure times tan phi dash plus UA minus UW, this is matrix suction at failure, times tan phi b. So, here as they came up with, Friedland and Morgenstern in 1977 came up with two stress state parameters that can be defined independently, and they confirmed Bishop's modified MC criterion. So, same stress state variables are used in this extended MC criterion. So, in this extended MC criterion, which is nearly similar to the Bishop's modified Moore-Coulomb criterion, which I can write it for you here. Tau f is equals to C dash, this is same at psi m equals to 0, plus sigma minus UA tan phi dash plus UA minus UW times xi f tan phi dash, because it is written as sigma minus UA plus xi f UA minus UW, that is effective stress, times tan phi dash. So, when we write as two terms by multiplying tan phi dash, then you get this. This first term is same, second term is same, third term there is slight difference. The xi f tan phi dash is modified to be tan phi b. Even though it appears to be a small difference between these two equations, there is a significant advantage in writing this Bishop's expression into this particular equation. That is, when you draw shear stress on y axis, that is tau f or tau, and net normal stress on x axis, then the extended MC criterion says that the shear stress for unsaturated soils can be defined with a surface or plane. So, this plane represents this particular equation. So, if it is tau f versus sigma minus UA, so then these two terms on the right hand side, this particular expression is valid. So, as C at x at psi m equals to 0, so here that is a C dash, this particular z axis on UA minus UW, this is 0. So, then this particular thing is not there, then you plot sigma minus UA and shear stress. So, when you plot, so the linear relationship is this angle of internal friction phi dash, and this is sigma minus UA axis, and this is tau f axis. This is a cohesion intercept. So, this is cohesion intercept and this is angle of internal friction. So, this equation is valid. And if you happen to plot tau versus UA minus UW, that is, when you look at this three-dimensional plot from this direction, then net normal stress will not appear for you, and then this can be plotted as this. So, that is tau f versus UA minus UW, this versus UA minus UW, then you have some C dash, and this angle is phi b dash. Tau f versus UA minus UW, this is how it is plotted, because on this tau f versus UA minus UW, the sigma minus UA is 0, because on this two-dimensional plot or two-axis plot, this sigma minus UA is 0. Therefore, this is simply tau f versus UA minus UW can be plotted in this manner. You have an intercept and you have phi b. So, if this is plotted at one particular sigma minus UA, which is more than 0, then this intercept becomes some intercept C1 dash. Similarly, if tau f and sigma minus UA are plotted at one particular UA minus UW, then you have some intercept. So, this is not equals to C1, C dash, this is equal to C1 dash or C2 dash something. So, this angle is phi dash. So, the graphical representation of stress state of the unsaturated soils can be very well defined using this particular form of Moore-Coulomb criterion given by Fredland et al. Let us understand how to estimate the shear strength parameters. We have C dash and phi dash as the shear strength parameters for saturated soils. In case of unsaturated soils, you have C dash, phi dash and xif, C dash, phi dash and xif of say psi matrix suction using Bishop's Moore-Coulomb criterion. So, this is called modified Moore-Coulomb criterion given by Bishop. In case of Fredland et al. 1978, this is C dash, phi dash and phi b dash. This is a single value, this is not a functional form, but however xif is a functional form. So, because this is only one particular value phi b dash just like phi dash, so estimation is easier. So, let us understand how to estimate the shear strength parameters C dash, phi dash and phi b dash from the suction control direct shear tests data. We have 4 tests conducted. In test 1, the UA minus UW. In test 1, the UA minus UW is maintained to be 10 kilopascal and sigma minus UA at failure is equal to 100 kilopascal maintained, and tau of is shear stress at failure is observed to be 55 kilopascal. This is the direct shear test data. And test 2, UA minus UW is 10 kilopascal and sigma minus UA at failure is equals to 300 kilopascal and tau f is 150 kilopascal. In test 3, UA minus UW is 300 kilopascal, sigma minus UA is 170 kilopascal and tau f is 240 kilopascal. And test 4, UA minus UW equals to 300 kilopascal and sigma minus UA at failure is 295 kilopascal and tau f is equal to 300 kilopascal. So, this is how the direct shear test by controlling the suction is conducted. So, here in 2 tests the matrix suction is constant, which is maintained to be 10 kilopascal. Then the net normal stress is changed from the first test 100 kilopascal, it is changed to 300 kilopascal in the second test. And 2 more tests are conducted. By maintaining different value of matrix suction in these 2 tests, that is 300 kilopascal and 300 kilopascal, but the net normal stress is now changed from 170 in the third test to 295 kilopascal in the fourth test. So, we have these observations, tau f value, that is shear stress at failure for all these 4 tests. So, using this simple data, if you conduct 4 different tests, then you will get all these strength parameters estimated. But in case of Bishop's Moore-Coulomb criterion, to obtain the Bishop's strength parameters, we need to conduct series of tests for getting a smooth variation of xif with respect to matrix suction. So, if you have wide range of matrix suction values, so that may vary in your soil, at all these different matrix suction data points, at all these different matrix suction values, the XIF need to be estimated by conducting so many number of tests, and then XIF can be estimated. Because here the phi b is a single value and this is not a functional form, so therefore just simply 4 different tests if you conduct, you get all those 3 Fredland strength parameters estimated. So using the first 2 tests, using Fredland's equation, when UA minus UW is constant, so under particular UA minus UW, so then the plot is between, if you recollect, so the plot is between tau f and sigma minus UA. So this is at one particular UA minus UW. This UA minus UW is not 0. So it is at one particular matrix suction. So then the angle is phi dash at one particular UA minus UW. The angle is phi dash and the intercept is C1 dash, some value, because if the UA minus UW is 0, then intercept is C dash, but this is some other intercept because we are plotting at one particular UA minus UW. So therefore this equation is simply tau f is equals to C1 dash plus sigma minus UA at failure and tan phi dash. So if we substitute from these 2 tests, this is 150 is equals to C1 dash plus sigma minus UA is 300 tan phi dash, and here this is 55 is equals to C1 dash plus 100 tan phi dash. So if we solve these two, that is if you take difference of this, then this is tan phi dash is equal to 95 by 200. So phi dash is 25.4. Phi dash is 25.4 degrees. So you already got one strength parameter. So from this, if you substitute this value here, you can get C1 dash as 7.55 kilopascal. Similarly, if you solve these two, so here at 300 kilopascal, this is at UA minus UW is 10 kilopascal. Here this is at UA minus UW of 300 kilopascal. So now tau f is 300 is equals to, this is C2 dash, because this is a different matrix suction value. So the intercept will be different. So therefore C2 dash is different from C1 dash, plus sigma minus UA is 295 tan phi dash. Yeah, this is 240 C2 dash plus 170 tan phi dash. If we solve these two by subtracting from one to another, we get phi dash equals to tan inverse 60 by 125, which is equals to 25.64 degrees. And if you substitute this value, you get C2 dash as 158.4 kilopascals. So as phi dash, we generally assume that it is constant, it doesn't vary. even with change in the matrix section. So phi dash we can average it out. So phi dash is equals to average of 25.4 plus 25.64 divided by 2. So we can consider this to be 25.52. So this average value we can use. So coming to the first intercept 7.55 kilopascal and second intercept is 158.4 kilopascal. From the equation tau f is equals to c dash plus sigma minus ua f tan phi dash plus ua minus uw at failure times tan phi b. So far we have utilized only this part. So now when this is plotted as tau f versus ua minus uw, you get some intercept here and here this is phi b. So this intercept changes. So this intercept is c1 dash, and where ua minus uw is equals to 0, this becomes c dash, and at different ua minus uw, say initially ua minus uw is 10 kilopascal, this is c1 dash, and at ua minus uw of 300 kilopascal somewhere here, this is c2 dash. So this is c1 dash, this is c1 dash, and this is c2 dash. So therefore now c2 dash, which is equals to 158.4 kilopascal, the expression is c dash plus ua minus uw, that is 10 kilopascal times tan phi b, 300, and the other expression, the c1 dash is 7.55 is equal to c dash plus 10 kilopascal is the suction times tan phi b dash, phi b. If we solve this, we get phi b is equals to tan inverse of 150.86 divided by 290. This is 27.48 degrees. So if you substitute this value here, then you get c dash is equals to 2.35 kilopascal. So the strength parameters are c dash equals to 2.35 kilopascal and phi dash is equals to 25.52 degrees and phi b is equal to 27.48 degrees. So these are the Fredlin-Toll strength parameters from the extended MC criterion. So this is how the direct shear test data can be analyzed for understanding the shear strength parameters from the extended MC criterion. So here the same expression can be used. Only 4 test data are required to analyze the whole data, and then if this is available, this set of data is available, so entire surface can be plotted, and at any given point, at any given matrix section value, at any given net normal stress, the shear stress at failure can be obtained. Very easy to do because we already analyzed graphical technique of representation of stress earlier. So now this will be easy to do it graphically. So once you take a graph sheet and then give proper dimensions for the x-axis and y-axis, So here the x-axis dimensions are varied up to 320 kilopascal because net normal stress in our case varies up to nearly 300 kilopascal. So similarly the shear strength tau f is also varied in this particular manner, and here the initially the net normal stress sigma minus ua at failure and tau f are plotted. So because the matrix suction is not 0, you do not have any test conducted at fully saturated state. So the matrix suction varied for two different tests, one is at 10 kilopascal and another one is at 300 kilopascal. Therefore you have an intercept which is C1 dash, not C dash. So how to obtain this C1 dash? Now one particular test data, that is at UA minus UW is equal to 10 kilopascal, you have two tests. From these two tests, the sigma minus UA, that is the net normal stress, is 100 kilopascal, this is 100, corresponding to the shear strength of the soil is 55 kilopascal. So 55 is here. So this is 60 and this is 55. So this is the point. And second test at the same matrix suction is conducted. So because tau f sigma minus ua on x axis and ua minus uw on y axis, z axis, then at one particular ua minus uw, so when we plot at one particular ua minus uw, that is 10 kilopascal, this is what we are plotting. So here if the ua minus uw is 0, then intercept is C dash, but here this ua minus uw is not 0, therefore the intercept is slightly higher than that, because and this angle is slightly different. So if C dash is same, then this is the thing, and if it is slightly C dash is increasing with increase in the suction, so this angle is 5b, that is what we got. So therefore here one particular net normal stress at ua minus uw corresponding tau f is given here, and another point at the same matrix suction value, that is at 295 kilopascal, the tau f is 150 kilopascal. This x axis is 300 and y axis is 150, and here x axis is 100 and y axis is 55. So now if we join this line with a straight line, the angle is phi dash and the intercept is C1 dash. So this is the intercept. This is same as what we got by solving those two equations. Similarly, other two test data, that is test 3 and test 4 are taken. So another graph sheet is taken and the axes are noted down on x axis and y axis. X axis again, this is sigma minus ua at failure, and y axis this is tau f. Now when this is plotted, one particular value of sigma minus ua, that is 170, and tau f at failure is 240 is plotted, and another point, sigma minus ua from the fourth test is 295 and tau f is 300 kilopascal on y axis. So when these two are connected with a straight line, you get C2 dash, that is intercept at ua minus uw of, this is at ua minus uw of 300 kilopascal. So the intercept is 158.4 kilopascal and the angle, this is again phi dash, is 25.6 degrees. So in the earlier this is UA minus UW is 10 kilopascal, and we got one C1 dash and phi dash, and when at UA minus UW at failure equal to 300 kilopascal, and you get 158.4 kilopascal as intercept, and phi dash is 25.6. So when we take average, we get the angle of internal friction average value, that is from earlier 25.4 plus 25.6 here. If you take average, you get 25.5. So this is phi dash. Now we have the other axis, that is shear stress tau on y axis and matrix suction UA minus UW on x axis. Then the first intercept, that is C1, is 2.3 kilopascal, and other intercept, that is 158.4 kilopascal. This is y axis for the matrix suction of 300, and here 10 is matrix suction, therefore x is this one and y is this. So from this, if you join these 2 points, you get phi b angle and the intercept, which is 2.3 kilopascal. So the C dash, that is cohesion intercept, is 2.3 kilopascal, and phi dash, which is already an average data which we used from the 4 tests. From the first 2 tests we got one value, and the other 2 tests we got another value. So from this average we got 25.52 degrees, and phi b, which we got from these 2 intercept values at 2 different suctions. So that is 27.48 degrees. This data is same as what we got analytically by solving those equations. So this particular problem can be solved using either graphically or by simply solving those equations by substituting test data from 4 independent tests. So thank you.